explicated above for omega equals 1/3, 0, and -1. So now that we have more tools at hand, basically to describe dark energy as well at this time, as far as a density goes, or a number of possibilities of density goes, well, we can actually now think about a matter radiation equality epoch of the universe. There might have been a time in the universe where pretty much things were equal between matter and radiation. So let's talk about that. So the epoch at which the energy density in matter equals that in radiation is called matter radiation equality. It has a special significance for the generation of large-scale structure and for the development of CMB anisotropies. So we keep mentioning about the CMB anisotropies, even though the CMB is considered to be largely smooth, but there are at higher orders considered to be or found to be some perturbations or anisotropies that are actually kind of important. So these, because perturbations grow at different rates in the two different eras, so matter dominated era versus radiation dominated era actually have different implications in terms of these perturbations. It is therefore a useful exercise to calculate the epoch of matter radiation equality. To do this, we need to compute the energy density of both matter and radiation and then find the value of the scale factor at which they were equal. So remember that scale factor A comes back here. So we basically are going to set this rho, or the total energy density in radiation, over the energy density or the critical energy density, to be equal to omega r over A to the 4. And to calculate the epoch of matter radiation equality, we will take these, equal them, and you get a certain redshift or a certain expression at which this happens. So as the amount of matter in the universe today goes up, the redshift of equality also goes up, right? For our purposes, it will be very important that the redshift of equality is at least several times larger than the redshift when photons decouple from matter. Thus, we expect photons to decouple when the universe is already well into the matter-dominated era. Okay, so we will summarize all of this in just a second here. Let me well, there are different evidences of dark matter. I would want to ask which one are you talking about. Then we would get some more context of what question you're asking about dark matter, Ajay. But yeah, dark matter is indeed something that we don't understand. So Americans valued women. Oh. Okay. So let us summarize the cosmic ingredients, okay? Number 1 was photons. Photons in the universe have a Bose-Einstein distribution because photons are bosons. They follow Bose-Einstein. With zero chemical potential, so their energy density can be determined by measuring their temperature. Yay! And we do have a measurement of their temperature from the cosmic microwave background radiation. Neutrinos, that was a cosmic ingredient as well that we discussed, have a Fermi-Dirac distribution. They're fermions, also probably with zero chemical potential, but there is some ambiguity in their energy density because of our ignorance of the neutrino masses. They're incredibly hard to measure, but we do have more knowledge about them now. Early on, this ambiguity is irrelevant since the temperatures are so much larger than the masses and neutrinos behave relativistically. Thus, the uncertainty in neutrino mass does not affect Big Bang nucleosynthesis at temperatures of order 1 eV. The we will look at my cat in just a second here. my children who are cats. In just a second here.